Welcome to the Embedded Frontier podcast, where we explore modern embedded systems development techniques so that you and your team can develop faster, smarter firmware. I'm your host, Jacob Beningo, founder of Beningo Embedded Group, the Embedded Software Academy, and co-founder of the Embedded Online Conference. In today's episode, we are going to be talking about one of my favorite topics, and that is simulation for embedded systems. This is a modern technique that I think every embedded software team should be embracing. And honestly, I see it as a hit and miss throughout our industry. I see a lot of folks who say, oh, simulation isn't necessary, yada, yada, right? But then I do see some teams that when they actually embrace it and learn to understand how to use simulation effectively, it can dramatically improve the way that they develop their embedded systems. And so today what we're going to talk about is all about simulation. This is what I consider to be the seventh step that any team should be following in order to modernize their embedded systems today. And what I'm going to do is we're going to talk about what simulation is, the different types of simulation, and then for those of you that are watching this maybe on YouTube, instead of me just being a talking head, what I'm actually going to do is show you a little simulation of a very common device on every embedded system, or not everyone, but many embedded systems, and that's a button. So I'm going to show you how we can actually develop a push button module and simulate that the algorithm works the way that we expect it to. Okay, and I'm going to give you a little bit of a preview for what we're doing next time. The next step would be to, in your modernization efforts, is to adopt artificial intelligence. And this is actually a push button module that I created using AI, but we'll go into those types of details a little bit later in the next episode. Today, I want to really talk about why simulation is so important to us embedded software developers. Now, traditionally, what we've done as embedded systems developers is we get our hardware and we start developing software for that hardware. Oftentimes, we start on a development board. We tightly couple our software to the actual hardware we're working on. Now, we've talked in previous episodes as part of our 7-step modernization framework, where we're modernizing our build system and modernizing our architecture. A good modern embedded software architecture decouples our application code from the underlying hardware. Okay. Now, that doesn't mean that we're adding all kinds of extra abstractions and latencies into our software. It simply means that we're using zero cost or low cost abstractions to make it so that we can write code that's reusable and decouples the core logic of our system from the underlying hardware. And while we have talked about that, it enables DevOps. It allows us to do stuff in the CI/CD pipelines. And we saw last time that it also helps us with test-driven development. What you're going to find is when you have a good modern software architecture, it also allows us to leverage simulation. Now, simulation is by no means something that's new in embedded systems. I have colleagues that I've talked with and worked with over the years who back in the 90s were writing C code in such a way that they could simulate a lot of their embedded systems without the hardware. Because let's be honest, the hardware usually shows up later in our development cycle. Oftentimes, we're not starting with hardware available to us. There are certainly exceptions, and I've had that happen on multiple occasions, including most recently on several other projects I'm working on. But the idea with simulation here is that it allows you to move your project forward, validate your software, get your software in front of end users before your hardware is actually available. Oftentimes, hardware and software kick off together, or software kicks off after hardware, or software they kick off at the same time. And so what you find is that you don't have the hardware available to you. So what we do in those particular instances is we can actually take our application code and we make sure that it's not dependent on the hardware. Instead, we make sure that it's dependent on an abstraction, okay? And then the lower line hardware, which let's say might be a driver for, let's say, a push button, the underlying driver that might read a GPIO or go on an I2C bus or a SPI bus or whatever it is, what will happen there instead is that the drivers will provide what the interface is expecting, okay? So our application code is dependent on the interface, and then our implementation is providing the implementation for that interface. And this is one of the solid principles. It's the dependency inversion principle, okay? And so we can decouple our hardware that way. Again, this is kind of software architecture principles that I think go well with a modern embedded system. But what this does, again, is it enables us to simulate the device, okay? Now, I wanted to use a push button as a primary example this week. And the reason for that is that I think every embedded systems engineer at one point or another has written a driver to debounce a push button. Push buttons are extremely common, right? And as many of you know, many mechanical switches, they're not all made equally. Some will have a debounce time of 5 milliseconds. Some will have a debounce time of potentially seconds, okay? A wide range there. Sometimes you need to be able to detect just a press and a hold. Sometimes you need to detect multiple presses, right? And certainly we could, write a module that reads a GPIO or uses an interrupt-driven system, right? That is going to detect whether the state of the I/O line is high or low or whatever it happens to be. There's multiple ways that you can have switches, in an embedded system, including like over I2C and SPI. But ultimately, if we write our code nicely so that we can abstract out that low-level hardware, we can actually simulate those presses and feed the simulated data into a debouncing algorithm for a push button that would allow us to validate the behavior, okay? Now, this is a type of simulation known as functional simulation. So what we're doing here is we're literally just abstracting out some code, and then we're providing a separate implementation that matches the interface that our code is expecting, that allows us then to inject different values and validate how our code is actually functioning. Now, this is a very common method of simulation. This really goes back, like I mentioned before, to the 90s, or maybe even before, okay, where we can just simulate that the hardware is there. And of course, you can imagine the great advantage there is that you're not dependent on the hardware immediately, right? And so oftentimes, if you're thinking about your architecture correctly, you can have some source that generates the data for your system. And for us, the push button, it might be a 1 or a 0, right? Whether the button is pressed or not, right? Or at least that's the GPIO state, right? Because there is a debounce. So we may see that the state of the GPIO could be 1 or 0, and we can collect that data maybe through interrupts over I2C or whatever it happens to be. And that is the beauty of using data, right? Because I can simulate that very easily by just either putting data into a file that's read. I could use a TCP/IP server to feed in values. I could even have a web page where I go and scroll or press a button, and it sends the state of that particular at that moment, whether it's a high or low, which could then feed to the system over TCP/IP into our system and validate our code generator. Now, I'm using something very simple here, a push button as an example there for functional simulation. But the beauty of this, of course, is that it does allow us to test nearly anything. Oftentimes, we'll have other subsystems that aren't available to us. Well, you can just as easily create simulations of those systems that allow you to validate your code. Now, before I'll say the advent of modern AI like Claude Code and Copilot and all of these types of different tools that are out there, oftentimes we would say, well, that's too much work. There's too much time and effort going into creating things that we're just going to throw away and we're not going to use anymore. But the truth is that today you could very easily spin off an agent to go and build you a simulator of a temperature sensor or of a valve controller or the data that would be provided by a push button. And very quickly you can get useful information that we can use to actually functionally test that our systems are working the way that they're supposed to. Okay, so functional simulation is a very useful and productive mechanism for us to be able to test our systems. Now, as I was mentioning a little bit earlier, I do have, for those of you watching on YouTube, a little bit of a demo that I can show you as an example of a functional simulation for a push button. Okay, so I'm going to switch over so that if you are watching, you can actually see my screen. And for those of you who are just listening to the podcast, don't worry, this isn't anything super critical that you are missing, but I'll kind of walk you through and kind of talk what you would actually see here. So on my screen here, I have a push button module demo. And what this is a simple C application that has a nice little graphical user interface that is keeping track of the state of a big button that says "click me" on it. Okay, on my screen. Now, what I've done in my code is I've actually created a push button module with a header and a C module. So I'm doing this in C. We could just easily do it in C++ and Rust or whatever your favorite language is. And what I'm doing here is I am creating a front end that is just detecting whether this button in my graphical user interface is pressed or not. And that data of, whether it's a 1 or a 0 is passed then into my push button module that then goes through my debounce algorithm, amongst many other things. As I mentioned, there's different types of active events that can be detected. So for example, there's a state machine that's running that's detecting whether the state is not pressed or pressed. By default, it's not pressed. And then it's telling what the raw input is. So right now, it kind of says, is the push button pressed? No, it's false. It's not pressed. It would turn to true if it was pressed. And then it's telling you the state of other parts of the state machine, which is, are we currently debouncing a press, or not? Okay. And then it's keeping track of some events like how many times the button's been pressed, how many times it's been released, and whether it's currently, same thing, event count for holds as well. All right. And so, again, I don't have a push button connected to a board. I could be working with a vendor and I could certainly do this on chip and have to, flash my code and do all that kind of stuff. Instead, what I have here is a simple host-based simulation where I can come over here and I can click on the actual simulation and I can see that's pressed. It goes through and it debounces, and it shows us what the state of the raw input is. And right now, I'm actually holding it down. We can see here it's detecting that there is a repeat held state that's currently occurring. I've pressed the button once, I'm holding it once, and then when I release it, it detects one release, and it says, hey, we're currently back in a non-press state. Inputs are false, and so on. And so what I can do here is very easily, I can press it again, see what happens with the states, how it's detected, hold it long enough until it's past this configuration point for being held. And again, I can fully flesh out and test my push button C code or C++, whatever I want to write it in, and I don't need the hardware to be available to me. Now again, real simple functional simulation, but again, we can do this for any type of sensor or any type of input into our embedded system that our application code is dependent upon. If I decouple my debounce code from the physical hardware itself by having a nice modern software architecture, this opens up the avenue to use so many different modern techniques to develop my embedded system. And ultimately what this allows us to do, it allows us to work faster. I think it's smarter, and it certainly allows us to deliver firmware much more efficiently and cost effectively. All right, so this was, I think, a pretty interesting example of how we can use a push button. And for those of you who are maybe listening in, what you're going to find is on my YouTube channel here, I'm actually going to be going through and doing a couple of videos around this little simple project of a push button. So I'll be talking, I'll have a couple of videos around, simulating the simulation piece of this, along with how I used AI to actually generate the low-level code. What worked, what didn't work, and that sort of thing. So if you attended my design news workshop a couple of weeks ago in January of 2026, you will have actually kind of seen some of this before, but that's okay. Most of you probably have not seen it. And again, we're talking about simulation and how this can affect our development for embedded systems. Now, again, by doing this, I wasn't dependent on hardware. I could do this for anything that I might want to simulate in an embedded system. So this is an idea of functional simulation. Now, functional simulation is great to kind of try to throw, curveballs at our embedded system for states that we might not be able to easily reproduce or produce in our hardware in the first place. But there are other types of simulation as well. For example, there is actually on-chip simulation where you would be going through and simulating the actual architecture of your processor. In these types of simulations, you might use a tool like QEMU or Renode. And what these tools allow you to do is say, hey, I'm running on an NXP MCXN947, for example, or an STM32 F4, or pick your favorite development board, right, or favorite processor. And what it does is it actually simulates the instruction level instructions that are executed on your chosen microprocessor. Now, these, of course, can be extremely powerful and useful. But what I have also, what I've also found is that the tools usually that do this the best generally tend to be a little, you actually have to pay for them and that sort of thing. Okay, so what you'll find is that they can be expensive if you're doing on-chip simulation. There are, like I said, though, open source tools like QEMU, which I have found to be useful, but oftentimes incomplete when you're looking at embedded microcontrollers. If you're working on Linux-based systems, QEMU is fantastic, but for, like I said, microcontrollers, generally I find it's incomplete most of the time when we start to look at the peripheral sets of the microcontrollers themselves. So if I want to be able to simulate serial communication, that could be a problem, or I2C bus or CAN bus and other peripherals like that. Okay, so it can be a lot more challenging, which is why oftentimes the tools that do that fully generally tend to be a little bit more expensive when we're looking at those types of simulations. Now, that's not always true. Renode is actually a super interesting tool that's open source. You can just go and kind of you create the configuration files and run simulations and run your code with Renode. You'll actually find that the Zephyr project uses Renode quite a bit to test a lot of their code as well. And you can actually develop your embedded systems and your application code building on top of Renode's simulations, which I think are actually pretty cool. But I'll be completely honest, most of the time I use functional simulation for a lot of the embedded systems that I work on. I don't necessarily need to validate that things are working on a given architecture, right? I can cross-compile my code, and I really should be doing hardware and loop testing anyways to prove that the system actually works on the hardware. And so while on-chip simulations can be very useful, for the most part, I find them to be, for many systems, overkill. Okay, functional simulation, I think, is maybe the key simulation technology that I hope every team takes a look at. Now, on top of that, there are certainly other types of simulation. For example, you can actually simulate your software architecture. And probably one of the most common simulations for software architecture is when we look at state machines. Oftentimes, embedded systems are broken up into various states of behavior. And what we're going to do with those states oftentimes is we want to be able to validate that, hey, the system actually moves through those states as expected. And there are certainly many tools out there that can do that. You can look at commercial tools like IAR or MATLAB. They both have tools that are capable of producing state machines that you can then go through and simulate in a visual environment. Oftentimes, those tools then allow you to simulate the actual behavior of your state machine. And then what you do is you can actually deploy or generate the code that state machine is associated with. So not only are you simulating the behavior of your system in those situations, you can also design the state machines oftentimes using a visual representation using UML diagrams and then generate the code that goes with it once you've validated it within the simulation environment. Okay, so those are certainly three major types of simulation that I find can be extremely useful for embedded software engineers. Now, you might be saying, Jacob, this is great. You know, simulation, the idea of being able to write my code and validate it before I have hardware is fantastic. But how do I actually get started doing this, right? Maybe you have legacy systems. Maybe your architecture is currently a little bit more tightly coupled than you would like. Well, one of the things that I have done when I work with legacy systems is I'll actually go through and help teams to decouple areas that maybe are higher risk where we actually want to run simulations on the application code. We work and we decouple those areas from the low-level hardware. So oftentimes it starts out by re-architecting your software in a way that you remove those dependencies on the lower-level hardware. Okay. Once you're able to do that, then you can write, you can write your own code for simulation, or you can go through and use artificial intelligence tools to generate a lot of that code for you. A lot of times the functional simulations that I'll run, I'm running Python scripts, truthfully, or I'm communicating over TCP/IP socket. Okay, when you're looking at functional simulation, you'll actually find that socket communication is a lot more deterministic and fairly fast, and you can easily substitute that in place of like CAN bus or some other interface if you've designed your interfaces in your architecture properly. And so you can actually swap those components out, and then you can feed that data into the bus and just watch your application execute. So my recommendation is you start really simple, okay? Maybe try simulation on a side project. Come up with something like a push button. Maybe you'll have some other idea of something that you want to build. And if that ends up being the case, that's perfectly fine. I think a push button module is just an example I thought of because everybody's familiar with it. But you could easily have a simulation of, there's all kinds of stuff you can do. Weather station could be an example where you have core code that monitors the weather. And then you feed in pressure data, temperature data, humidity sensor data. You can create simulations of those sensors and feed it into whatever the weather station would do and have it push up to the cloud and see the data over MQTT messages or whatever you want to use and kind of validate that, hey, look, I could create my own little custom weather station for fun, right? There's so many different ways that you can leverage simulation. And while we think on the embedded frontier, we try to think about modern technologies that we can apply to embedded systems. simulation, it's not modern. It's something that's been around for a long time, but I find many embedded systems teams ignore it. And as we start to move into an era where AI is far more prominent and we're leveraging it to really develop our systems, the more you can leverage simulation to test things and validate it, I think the better off you are going to be. Okay. And so, make sure that you're thinking carefully about these modern development techniques that will take you to the frontier of developing embedded systems. Okay, so with that in mind, I do want to remind all of you that the Embedded Online Conference is going to be taking place May 11th through the 16th. There are actually discounts of like $150, I think, right now for the conference if you register before the end of February. So I'd highly encourage you to go over to embeddedonline.com and get your conference pass now. There's also an archive that's available from all the years that we've been putting on the conference. All those talks are still available in the archive. There's a pretty big discount right now for that as well. That gives you access to a whole bunch of different talks. Okay. And this year, Stefan and I are in the process of putting a whole bunch of new features into the conference platform. I don't want to share what those are quite yet because they are still in development. But let's just say that AI is going to be helping you a lot in the Embedded Online Conference this year, because we've often found that people don't have time to watch every talk. And so we've come up with some interesting ways to help you guys learn what you need to as fast as possible so that you aren't necessarily sitting through, long talks and that sort of thing. But we actually have 10 different workshops that we're going to be running, ranging from, how you can refactor your legacy code, how you can use AI, and many other really cool workshops this year. So I highly encourage you to check that out. And from there, what we're going to do in the next, podcast is we are going to talk about artificial intelligence and machine learning and how we can apply it to embedded systems. And so while today's podcast is a little bit on the shorter side of things, next week's is probably going to be extra long because I have so much to share with you on how you can improve the way that you develop embedded systems using AI and machine learning. And so, keep an eye on my Embedded Bytes newsletter, on my website, on LinkedIn. There's going to be a lot of content that I'm going to be sharing about how to use artificial intelligence. It's an area I'm really excited about. Super cool technologies. There's some stuff I was doing just before this that honestly just kind of blows my mind what these tools can do and how fast they can help you develop systems. But that's going to be for next time. In the meantime, I want to wish you a great day and happy coding.